Yesterday we discussed cylindrical coordinates, which is a coordinate system based very directly on polar coordinates. Today we're going to be talking about spherical coordinates. So spherical coordinates are used when you have an even more symmetrical, or they're useful when the surfaces you're creating are even more symmetrical, meaning they have more lines of symmetry through them than a cylinder would. So again, it's a 3-coordinate system because you're graphing these in 3D. So the first coordinate is rho, so that's the Greek letter rho, and then theta. Theta in cylindrical coordinates is the same as theta in spherical coordinates, and then we have phi or phi. I don't know which one it is. I've heard it both ways. We could call it phi. So some Greek letters there, actually 3 Greek letters there.
Wait, you did, is it, we did the Greek last year, Mark. We did it last year.
Yeah, is it phi or phi?
I think it's fine.
Phi. Okay. So first there is rho, and rho is defined as the distance from the origin to the point. So it's just an as the crow flies distance from the origin to the point. Rho is defined as a positive or non-negative quantity, greater than or equal to 0. Theta is the same theta that we used when we were dealing with both polar and cylindrical coordinates. It is the angle that is made with the positive x-axis as you create a shadow of that line in the xy plane. No restrictions on theta. Theta can be positive or negative. And lastly, we have phi. Phi is the angle between the positive z-axis and the line from the origin to the point. And phi, at most, can be pi. Little assonance there. So this particular coordinate system uses 2 different angles instead of other coordinate systems which only use maximally 1 angle. So it's a little more rotational heavy in terms of the geometry. Yes?
The angle theta is like measured along the xy plane, basically.
It is measured in the xy plane. So you look at, let's say the point that I had was right here. If we consider a line from the origin to this point, and the xy plane was the floor, it would be the shadow of this line's angle that is made with the positive x-axis. That is theta. And I'm going to bring up a diagram that will hopefully bring a little light to all of this. So here's your diagram. We have our point, rho, theta, phi, which is right here. And you can think of it in terms of its rectangular coordinates as well. So the way you do it, or at least the way I do it, is I take a, I don't know, yardstick, whatever, of length rho, line it up with the positive x-axis, rotate it theta degrees, and then what I do is I go up towards the z-axis to line it up with the correct phi. So let's say phi, or let's say rho is the length of this yardstick, and this is the positive x-axis. Okay? What I do is I line this up. It's rho units long. Let's say my theta is pi over 2. So I'm going to rotate it pi over 2. And let's say my phi is pi over 6. pi over 6 would be the angle it makes with the positive z-axis. So that, in this case, is this corner here. So pi over 6 to the positive z-axis. So therefore, my point is about right here, about 60 degrees off that z-axis. Ali?
So you said theta was pi halves. Wouldn't that mean that was completely like along the y-axis?
I thought I said pi over 4.
Okay.
Sorry, that's what I meant. Yes, and so phi is going to only need to range between 0 and pi. 0 means it's on the positive z-axis. Pi means it's on the negative z-axis. So from where you are on the xy plane, you can rotate, well, you could be at 0, and that means you're on the positive z, or you can be at pi, and that means you're on the negative z-axis. Okay? And that's all you need to do is go, fully up to fully down, and that gets you anywhere above the xy plane or below the xy plane. So if phi is 0 to pi over 2, you're in the positive above the xy plane, and if it's less than pi over 2, all the way down to pi, you're in the negative part below the xy plane. All right, any questions on that? So here are our conversions, all based on trigonometry. So we have a conversion between spherical and cylindrical, and then we have a conversion between spherical and rectangular. So that's just using the geometry, the trigonometry that exists in the coordinate plane. We talked about how rho is the distance from the origin to the point. So we have rho squared, and this is just a version of the distance formula here. And then we have the trig. All right, you guys ready to do some conversions? So we're going to begin by converting coordinates, and then we'll move out to surfaces. So let's convert this point from cylindrical to spherical coordinates. It always helps me to label. So this is r theta z. And from the prior slide, we have some conversions. So to get rho is r squared plus z squared, or rho squared is r squared plus z squared. So rho is the square root of r squared plus z squared. So that's going to be the square root of 8, or 2 radical 2. Z equals rho cosine theta. Sorry, rho cosine phi. So that's radical 2 would equal 2 radical 2 cosine phi. So that means phi would have to equal pi over 3. I'll rewrite that. And I got that because of the inverse cosine of 1/2. And so I have rho, I have phi, and I have theta already, so that's great. So what I get is radical 8, or 2 radical 2 pi over 4, which is theta, and then pi over 3. So then to get to that point, again, let's pretend this meter stick is 2 radical 2 units long. I would rotate from the positive x-axis pi over 4, which is about our 45-degree angle, and then from my positive z, I would be about 60 degrees off. Okay, so about right here. So we know how high to go by doing that rotation with respect to the positive z-axis. Questions on that? All right, let's do the next one. We have Cartesian. So that's x, y, z. And then we know how to find rho. Rho is the square root of x squared plus y squared plus z squared. So it looks like our rho is 2. And then for theta, I like to do a little drawing. If x is -1 and y is 1, this is my point on the xy plane. You should always label your axes. So -1 for x, 1 for y. So it looks like our theta, which is our rotation from the positive x-axis, is going to be 3 pi over 4. Any questions on that? Okay, lastly, z equals rho cosine phi. So negative square root 2 equals 2 cosine phi. So we have negative square root 2 over 2 equals cosine phi. So that's going to be in our second quadrant. So phi is going to be 3 pi over 4 as well. So we write it as 2 theta phi.
Wait, so Mrs. Nolan?
Yep.
Or, just to like remember, inverse cosine is from 0 to pi, and then inverse sine is from negative pi halves to pi halves, right? Because I always like to get, like, if it's supposed to be negative pi fourths or like 3 pi fourths, like for.
So phi is defined as values between 0 and pi.
Oh, okay.
So you want to pay more attention to those restrictions than you do the cosine inverse restrictions. Cosine inverse 0 to pi. Yeah, because sine is negative pi over 2 to pi over 2. Tangent is 0 to pi? No, negative pi over 2 to pi over 2. No?
Tangent is
Look at, I pulled that out. Sorry, when you don't use that inverse trig stuff.
They just have to calculate.
All right, questions on converting coordinates. All right, so let's look at some surfaces. So you might want to have your definitions of rho, phi, and theta in front of you to think about this. So given your definition of rho, what would rho equals 5 look like? Xavier?
A sphere centered at the origin of the radius phi.
Good, because essentially you're finding all points that are 5 units from the origin. That's a sphere. Because anything equidistant is going to go in a circular manner in all directions from 0, 0, 0. Phi equals pi over 3. Think about what that would be. So you're taking your angle from the positive z-axis, it's pi over 3. always pi over 3, what are all those points going to be? Daniel?
It's off now from the phone.
Yes.
How do you spell now?
Put it in.
I got you.
And this angle is pi over 3. So that's pretty tiny. Good. How about theta equals 2 pi over 3? Ashley? That is a plane. So if you think of starting at the positive x-axis and rotating 2 pi over 3, I'm going to be in Mr. Reiner's room, but then I make this infinitely long and infinitely high. Okay, so I'm going to do it pi over 4 just so I'm in this. So pi over 4 would be like this, but it can go all the way from 0 down to pi in terms of our phi, and then it can go wherever we want in terms of rho. So it can be as long as it wants, and that just creates a big plane. Questions on that? How about rho sine phi equals 2? Ali?
Do you like just a circle? With radius.
All right, tell me about that.
So if you can convert between spherical and cylindrical coordinates, you know r equals rho sine phi. So it's the same thing as writing r equals 2.
Good.
Which is the same thing as writing x squared plus y squared equals 2.
Okay.
Which is the form or the like general equation for a circle centered at the origin.
Okay.
Why would it be 4? Would it be 2?
It equals r squared.
Oh yeah. So yeah, radius is 2, not 4. No, that's 2.
Does it equal r or r squared? Rho sine phi.
R.
So you have a circle, a radius 2. What are our limitations on z then? Is z addressed, Ellie? Yeah. So z can be anything. So picture us repeating this cylinder infinitely high on the positive z and low on the negative z. So this is a cylinder. Circular cylinder. Centered around the z-axis. Question on that? Actually, okay. So picture us for B going pi over 3 away from the positive z-axis. Okay? Now, that means I have to be along this angle, but I can sweep out anyway because theta is not limited. So this can sweep any way it wants and all the way around. Okay? Also, rho can be anything, so the distances can be anywhere. So going from the origin all the way out, but then you can take those lines essentially and just keep rotating them around. Daniel?
If you want to know, if the roll is pi thirds, wouldn't that mean it's the bottom half of the coin? Since it's greater than like a 90-degree angle. Oh wait, no, that's what it is. Yeah, pi thirds is less than pi halves, right?
It is.
Okay.
All right, we got it on tape. Just less than 50, Daniel. Okay, so spherical form is good for surfaces that have point symmetry, where all points are rho away from a single point in space. Just if you have that quality, the equations are very simple in spherical form. So that's why we can describe a sphere by just saying rho equals 5. Think of how complicated the sphere equation is in Cartesian. X squared plus y squared plus z squared equals 5 squared. Or we could just say rho equals 5. So the more symmetrical the shape is, the more simple those equations are going to be in spherical form. So you have some choices. Any questions? Xavier?
So one quick question just about the spherical coordinates. That angle from the z-axis that phi is can be measured at any theta, right? So even if you were in like negative, well, what would be like negative x and negative y in Cartesian, it's still a positive z.
Correct.
Still a positive phi from 0 to pi.
Yeah, you still rotate it from the positive z-axis.
Okay.
Okay, other questions? All right, here is your assignment.